Hello everyone, I'm Paul and today we're solving problem 1857, largest color value in a directed graph. This is a hard problem and here we will talk about topological sort, which is something we don't see very often in these problems, so keep watching for the intuition, approach and efficient solution. There is a graph, such as this one, where each node in the graph has a color, for example red, blue and purple, and we can have up to 26 colors. Why? Well, because we can have a color corresponding to every lowercase English letter, meaning we can have colors from A to Z. This is 26. We're given a string colors where each character corresponds to the color for every node. So, for example, we can get A, B, A, C, A, meaning this is color A, this is color B, this is color A, this is color C, and this is color A. And we are also given an nested array edges to represent this directed graph. Remember that in directed graph, edges move in one direction only. And here we need to return the largest count for any color in any valid path. So for example, we can have one path here and the largest count for any color in this path is 1. And for example, we can have another path here. The largest count for any color in this path is 1, 2, 3. Okay, so the maximum result that we can get in this case is 3. And if we find the cycle here, for example, if this 0 as an edge to itself, we return -1. Now we can take any path here. We could take this one, or this one, or this one, this one. But the key is here, we need to return the largest count for any color. Meaning maybe the best thing we can do is to consider valid paths from every source. And what do we mean with source? Well, a source has no incoming edges, has no in degrees. For example, 0 is a source. So given that we are trying to find the maximum count for any color, maybe the most intelligent thing we can do here is to start from every source. Okay, so from here we only have two paths. One here and one here. Now maybe with these hints you can get the solution if you have already heard of topological sort, and more specifically here we will be working with a BFS based topological sort, and more specifically we will be working with something called Kahn's algorithm. Let's see how this works. Let's say we have this graph. Now with this algorithm we will be able to iterate this in topological order. And in this type of order, to iterate a node, we first need to iterate every node corresponding to every in degree, meaning to every incoming edge. Let's see what this means. If we are trying to iterate this one, we first need to iterate every node corresponding to every incoming edge, meaning we need to iterate this one first. And if we want to iterate this one, we first need to iterate this and this. And if we want to iterate this, we first need to iterate this. So for example here, by the time we reach this node, we will already have the information of all of these nodes. So just to be clear, this is a possible topological order. We first iterate 0, we then iterate 1, then 2, then 3, then 4. Okay? So for example, by the time we reach 2, we have already iterated 0. By the time we reach 3, we have already iterated 0, 1, 2. Okay? Now we will also have this matrix or nested array or frequency map, whatever you want to call it, where we will use rows for nodes and columns for colors. And here we will store frequencies for each color at every node. So remember, we are starting to iterate this from the sources. We are starting from here and from here. Let's say we start here. So at node 0 we have 1 red. So in 0 red we add 1. Remember, every value in this grid is initially 0. And from this node we will update the information in every neighbor, meaning here in node 2, meaning here. And for every color in this node we will take the maximum of the current count for every color and the information in the parent node. So for example, in this case, at node 0 we have 1 red, so at the maximum between 1 and 0 is 1, so at node 2 we have 1 red also, and this is the 0 and 0. And finally we remove this incoming edge from node 2, and now this is also a source node. So now the next node in our queue is this one, and we will add 1 red at node 1. So in node 1 red we add a 1, and we need to update every neighbor, so we are updating this. So at node 3 we are adding this red, so this is now 1, and we remove this incoming edge from node 3. Now the next node in the queue is this one. This has no incoming edges, and we are adding to node 2 1 blue. So in 2 we add 1 to blue, and we need to update every neighbor, so we update these 3 again. So the maximum between 1 and 1 is 1, and the maximum between 1 and 0 is 1, and the maximum between 0 and 0 is 0. So now we remove this edge, and here at node 3 we have 1 red and 1 blue. The next node in the queue with no degrees is this one. So we add 1 red to node 3, so this is now 2, and we update every neighbor. So at node 4 we take the maximum between 2 and 0, this is 2, the maximum between 1 and 0 is 1, the maximum between 0 and 0 is 0. Next we remove this edge. The next node in the queue is this one, so we add 1 purple to node 4, so this is a 1. This has no neighbors, so we end here. And now we can get the result with this frequency matrix. We know that the maximum value we saw is a 2, so the result is 2. And finally, how can we detect cycles here? Well, we know that we went through 1, 2, 3, 4, 5 nodes. So we'll carry a count with us, and the count will be 5 by the time we end this, and we have 5 nodes. So in this case we return the result, but in case we have a count that's smaller than the amount of nodes we have, we return -1. This is how we can detect cycles. Because think about this, let's say we have one node, 0, that's red, and this node is pointing to itself. In this case here we have 1 incoming edge, so we will never add this to our queue. This means we'll have a difference between the number of nodes we have and the number of nodes that we can iterate. So this is it for the approach. Time and space complexity for this one will be big O of nodes plus edges. And now let's go with the code, and hopefully you will get the idea. First, n equals length of colors, and now we are building our adjacency lists and our in degree list. We can do this in one loop. So adjacency will be default dictionary with a default value of an empty array. We do this like this in Python. We use the word list, and in degree equals default dictionary with a default value of 0 for every key, and we do this with this word in Python. And now for AB in edges, and remember this is a directed graph, so adjacency list at I dot append B, and in degree at B plus equal 1. So now the node B has one more incoming edge, meaning one more in degree. And now we want to add every source node to our queue. So we can do this like this in Python. Queue equals a deck. We are using a deck because we want to pop elements from left. That's what we do with BFS. And in here we can build an array, and we can do this like this: node for node in range n if in degree at node is 0. Okay, so we are adding every source node, meaning every node with no in degrees, to the queue. And initially the result is 0. We will create a frequency matrix or a frequency nested array. We do this like this in Python. Frequency equals, initially we have an array with 0 times 26. These are the columns, these are the colors for every value in the range n. Okay, so just to be clear, this is frequency node color. We are using nodes for rows and colors for columns, and we will keep a count of the nodes we visit to prevent cycles, or to know when we have a cycle, so we return -1. So visit equals 0, and finally we will return the result if visit equals the amount of nodes we have, else we return -1. Now here in between, while we have something in the queue, this is like a regular BFS, so node equals queue dot pop left, and we will iterate every neighbor. So for neighbor in adjacency list at node, here is the specific part for this algorithm. We add 1 to visit every time we visit a node, and here we subtract 1 in degree from every neighbor. So in degree at neighbor, sorry, this is neighbor, minus equal 1. And if in degree at neighbor is 0, we can add the neighbor to the queue. And now comes the specific part for this problem. First, remember we have only 26 colors, and they are initially represented with letters, so we can transform every letter into a number from 0 to 25. We can do that like this: current equals ord colors at node minus ord a. Now we can update the frequency for the current node and the current color. Here we add 1, and we can also update the result at this point. Result equals the maximum between the result and the maximum in the current row, meaning the maximum in the row frequency at node. And now here we need to update the information for every neighbor. So for I in range 26, meaning for every color, frequency at the neighbor at the current color equals the maximum between this and the frequency of the current node at the current color. Okay, so this is it for the code, and now let's submit this and see if it works. As you can see, this works and it's efficient. And remember, you can also solve this with DFS. Here we used BFS. So if you found this useful, please drop a like, subscribe, and see you in the next one. Bye bye.